We're going to pivot now to the interesting topic of indoor air quality, very apt given the Saharan sands are all over us in the past few weeks. And I'm delighted to introduce to our next speaker, Dr. Pawel Misztal, who is faculty in environmental engineering from the University of Texas at Austin.
Thank you so much. And I'm delighted to be here, and I'm extremely excited to inspire our thinking about indoor air quality today. So I would like to acknowledge my wonderful research group, graduate students and postdocs, and also I would like to thank a lot of sponsors who have generously funded my research. And I will start from the question, have you ever wondered how much time we spend indoors relative to outdoors? Well, it turns out that the total time spent indoors is approximately 90%. That's shocking. And it can be converted to so-called Corsi code. And this is, what do these numbers mean? So these are years. So 79 is average life expectancy in the US, out of which we spend 69 years indoors, 54 at home, 26 in bed, 4.3 on commute, and actually only 6 years in total for outdoor air. And we worry about relatively clean outdoor air quality, which is regulated, and often not worry so much about indoor air quality, which is unregulated. So air quality is among 3 out of 30 causes of global ill health, so it's about 10%. And what I want to highlight is that exposures to adverse air quality occurs predominantly indoors. This is an interdisciplinary problem, and it requires collaboration between engineers, chemists, physicians, clinicians, and so on. And there is a lot of opportunities here to close the gap when going between source emission rates to actual health effects. And one of the landmarks of public health research is the famous 6 cities Harvard cohort study. And this study showed beyond doubt the link between air quality and human health. So as you can see, here, for example, the cities that had they were most polluted, the survivability rate is much shorter. But did you realize that when you prepare a stir-fried dinner, for example, the concentration of particles, and it's just fine PM2.5 particles, which is a fraction of total particles, can be so much higher. And I know it's acute, but this is what we don't think about. So I'll tell you a little bit more. And I will start from particle exposure. So we know that PM impacts, there is an impact on mortality. And the recent Lancet article mentions that there are approximately 2.7 million deaths due to indoor air quality. So to understand the health effects, we need to understand how the polluted air gets into our body through this nice system of our lungs. We have about 500 million alveoli in lungs where the gas exchange takes place. So with half a liter inhaled with each breath, we also inhale indoor pollutants. So there are thousands of different chemicals we inhale right now, and some of these pollutants can travel to alveoli and also to the bloodstream. The smaller the particle is, and I I'm showing here, for example, the PM 2.5 and PM 10, how it relates to the diameter of human hair. And the processes indoors are pretty complex. The indoor air environment is quite different than outdoor environment. And one thing that is different is that the volume of the atmosphere, of the outdoor atmosphere, is enormous compared to indoors. The volume of indoor spaces is so much smaller, so different pollutants can accumulate, and what's important is this Q, so ventilation rate. So this ventilation rate is basically an air exchange rate, so the rate, how many times the air is exchanged in space, and the volume, so the volume matters too. So what are major indoor air pollutants? And here I will show you some research from the UT Test House. We are very lucky at UT Austin to have this wonderful resource, and that UT Test House is one of the most characterized houses on the planet. So you can do whatever you like in that house. We hosted a large campaign. Top researchers from all over the world came to Austin, and what you can see here on this picture is basically UT Test House is surrounded by trailers with $1 million worth instrumentation that's basically looking at what people are doing. So it's a conventional, normal house, and we did something as cool as stir-fry experiments, but also there are many papers you can read from this campaign. And I will start from particles. So I don't have time to go through all the details in this graph, but what I want you to notice that each time there was some cooking event, for example, or cleaning event like mopping, the number of particles pretty much went through the roof. And it's the size, as I was showing you, the alveoli is important. And as you can see, different foods will generate different size distributions. And so, for example, if you look at the toast, it's shifted more to fine, and most others are ultra fine. The composition of particles on the right is also important for human health. So what about gases and gas phase pollutants? We know the famous Paracelsus quote is that the dose that makes the poison. And this is an important fact because we have, as I mentioned, we have thousands of pollutants that we are inhaling right now as you listen to this talk. And the abundance spans 9 orders of magnitude, but so does toxicity, atmospheric lifetime, and our level of understanding is skewed towards most abundant compounds. But the most abundant compounds are usually not toxic. For example, ethanol, acetic acid, these are compounds present in kombucha. I drink a lot of kombucha. I'm not really concerned about those compounds. I'm much more concerned about toxics, which are below the detection limit that we don't even realize that we get exposed to. So with better technologies that we have now, we are able to resolve even trace level of pollutants out there. The nice thing about gaseous air pollutants is that you can fingerprint pretty much every single activity, every single source, as you can see here, bleach, mopping, and stir-fry and have different signatures. But what's really, what's blowing away is that the outdoor air quality, this gray portion of the pie chart, is really minor compared to all the other sources that are indoors. And historically, we focused on characterizing emissions from building materials. But even building materials constitute less than a half of emissions. And it's cooking and humans actually dominate quite a lot. It's another half of the pie chart. So historically, the approach was to go to as many houses you can and do a snapshot. Just take a snapshot composition of indoor air. And this is one of those very nice classic papers showing select number of different volatile organic compounds, including toxic benzene, exposure to which is very well known and characterized. It's linked to leukemia and cancer. And what you can see on this graph is that quite a large portion of houses have very high level of benzene. And you might be thinking, oh, maybe those houses use a lot of benzene or products like paints and so on, which is probably true as well. But what this graph actually is reflecting is how well the spaces are ventilated. So the well-ventilated homes will have much lower benzene. But we can do a different approach. So the novel approach is to find just a few houses which are representative and continuously measure what is happening in different spaces. And here what we did in Oakland Hills, for example, it's a very nice house. We even wondered if we will see anything there. And for a period of more than a month, we continuously looking at those different spaces. So if you look at the average mass spectrum, so this is campaign average, more than a month, you can see that it's a quite complex, more than 200 different chemicals, and you can see things like consumer care, siloxanes from consumer care products, different benzenoids, furanoids, and lots of different compounds. So what we can do, we can sum up these compounds and show as the total VOCs. So this is the sum of VOCs on the y-axis, and this is about 1 month, and it's colored by carbon dioxide. So carbon dioxide originates mostly from breath. In the outer atmosphere, it's about 400 ppm. And what you can see here is whenever people are present, the concentration is super high. But do you know what's in here, this lowest point on the graph? Well, this is actually when occupants opened all the windows and all the doors. This was so-called ventilation experiment. So this is only when you can really reduce the concentrations to levels close to outdoors. And do you know what that period is? This is when the house was vacant. The occupants went for vacation. And so to present it on the DL pattern, like basically averaging the whole period of campaign, you can see that the outdoor air compared to indoor air, there's a huge difference. And if you look at other spaces, kitchen, hallway, it follows because there is a good mixing. So another way to look at it is to look at outdoor and indoor air when the house was occupied and vacant. So outdoors, it doesn't make a difference if people were present in the house. But as you can see, indoors, it's such a huge difference when the house is vacant, and the standard deviation from that average is absolutely huge. As you notice, it's a different scale. Do you want to see it on the same scale? There you go. The outdoor air is like zero air, literally. And therefore, I come to the question. We know now that the air, indoor air, is generally more polluted than outdoor air, but how to embrace complexity of human exposure to understand their effect on human health. And in my lab, we are discovery-oriented, and we really develop novel methods to look at air pollution. We have the very unique mass spectrometer called Vocus-2R proton transfer reaction time-of-flight mass spectrometer. And this is a long name, so we prefer calling it the sniffer. And the sniffer is really cool, and it's a similar instrument that we used in Oakland Hills that I showed you the data, but it's like the newest generation. It's like a Ferrari among the mass spectrometers. There are only a few of those in the nation. So just as an example, like schools have spent a lot of time, a lot of effort and funding, try to make spaces clean, and that's definitely a good thing. But the question is, should we care what's in our cleaners? Are there any risks of disinfectant exposure? So just when the COVID hit, we had this idea, we wanted to know what is happening when we disinfect spaces, what are the byproducts, and what is the role of masks. So we conducted quickly a pilot study and got funded. The PIs are Leah Hildebrand-Ruiz, Attila Novoselak, and myself. And also a lot of students had a lot of fun to work on this research. So I will just highlight some work of my outstanding PhD student, Daniel Blumdahl. And so basically to understand exposure, to quantify exposure, what you need is to measure concentration, but also what you need is time. So this area under the curve, if you, for example, want exposure for 1 hour, this area under the curve is equal to exposure. And if we use the dynamic mass balance model on indoor space, you can see what a huge difference it makes to this area under the curve if you have a tight envelope. So this is basically when you don't ventilate the space very well, and when you have more ventilated spaces. So definitely a huge effect of ventilation on reducing exposure. So what about the masks? Do they make things better, or do they make things worse for disinfectants? And here is on the upper graph shows dichloramine. It's one of the byproducts formed in bleach disinfections, and the open squares correspond to a concentration in front of the mask, and the closed circles correspond behind the mask. So you can see a huge reduction in exposure for dichloramine, which is relatively sticky. The monochloramine, it's lower reduction, but still. But after some times, there is accumulation on the mask. So what is happening if you don't get rid of the mask, the exposure actually from using the mask will be higher. So if you use the mask, you need to remember to dispose of it after the cleaning event. So one discovery my other student made on other project where he looked at microbial VOCs in indoor air, something that she discovered was that when we change relative humidity, so this is about learning about the fundamental process indoors. When we change relative humidity, which is generally the case, what it does is that this drying and wetting process, it results in higher emission of material degradation markers. So we can actually track degradation based on the specific markers such as morpholine type of compounds coming from polymer like nylon, for example. So, okay, so would the best approach be to actually measure pretty much everything in different air spaces? And do we measure everything? And the question is that it's not sufficient, I think. We also need to monitor some metabolites. So basically, we could monitor blood for some air toxics that we got exposed to. But there could be some other novel methods. For example, in my lab, we have a breath inlet, and we can look actually at breath metabolites. So human breath analysis seems super promising, and this is a quite complex graph, but I want to walk you through carefully because it's really, really cool. So this is a log concentration ratio of exhaled air to inhaled air. So what you see on the upper portion of this graph is what is enhanced in breath. So as we expect, we see metabolites such as isoprene coming from sugar metabolism, acetone coming from lipid metabolism, and so on, and also lots of other metabolites. But another cool thing is that we don't just exhale endogenous metabolites, we exhale pollutants that we get from the environment. And because our inhaled air is not clean air, we also exhale air toxics, actually, such as aromatics and for example, here is D5, decamethylcyclopentasiloxane. These are compounds present in consumer care products, for example. So because they are present indoors, we exhale them, but we don't exhale in the same amount, like with nitrogen. We exhale depleted amounts. So what does that mean? Where do these compounds end up? So we also measure we are able to measure liquid and solid materials. We develop new techniques to measure things like flame retardants or different endocrine disrupting chemicals such as phthalates and plasticizers. And one amazing thing which has not been thought about much is human hair is amazing biological material. Hair grows at a relatively constant rate of ½ inch per month. And it actually accumulates some compounds to higher levels than in the blood. Has been used in forensics a lot. So we're thinking, we did a pilot study, and Anna Neville led the study, a grad student in my group. And what we found, pretty amazing, this is just a thermogram, so we heated her in a thermal desorption tube. And what you can see for the low mass compounds, some of them get evaporated completely. When you look at higher mass, more semi-volatile compounds, they increase with temperature. So when you segment the hair according to past history of exposures, for example, and here's just an example for dibutyl phthalate, which is an endocrine disrupting chemical. And Anna, she was wondering why the exposure was so much higher in the 4 months prior. And what she associated with, and this is just a hypothesis, is that, well, it was exactly coinciding with her visit to her parents' house, and what they were doing was the remodeling of the house, and so potential exposure source. But what's the solution to the pollution? And we cannot control all the sources. Source control is definitely important. But because we cannot stop exhaling, cannot stop certain emissions, we need to have good ventilation systems. And at UT Austin, we have the amazing full-scale HVAC system where we can study chemical processes, ozone-generated, the different byproducts, and also how efficient the filters are. I won't go through all the details, but this is just an example of an extremely efficient filter. You should, if the filter is efficient and it's compound specific, you should see everything on the left. And this is the filter that is used in surgical theaters, in clean rooms, and so on. So anyway, just to summarize, the fact that the indoor air quality is unregulated, it doesn't mean that it has no effect on human health. We need more studies. We need novel measurements, both of acute exposure and chronic exposures. And we need to quantify the link between exposure and human health. And in my lab, we are pretty much obsessed with fingerprinting all the different sources. You know the saying, you don't walk to the same river twice. And I'm saying you don't inhale the same air twice. So with that, we also have specific sources of exposure, like communities living close to oil and gas. And we also work to understand exposure of firefighters when the house is on fire. So with that, I would like to again thank all my research group and sponsors, and thank you all for your attention.
Thank you, Dr. Misztal, for that interesting talk. We have time for maybe 1 or 2 questions. Please identify yourself.
So very informative for somebody who is not a practitioner in this topic. I was a little confused by one of the graphs. If you could go back to it, this was about the benzene exposure I guess it was probably like your 10th or 12th slide. I think it said percentile and micrograms per, yeah, this one. I was kind of confused. If you could explain this graph a little bit better so I have a better understanding.
Okay, yeah. So this is like percentile of homes. So, for example, here you would have the median, right? So the top, so if you had like 2,000 of different homes, so you have a few hundreds which would have, so somewhere here is the recommended level for benzene. So a lot of those houses would have exceeded those benzene levels. But because these were snapshot measurements, it could be that they were taken at different times of day when people were preparing dinner and so on. And yeah,
so in other words, 100 percentile homes have 16 microgram per meter cubed?
So this is like basically the level of exposure in different homes, yeah. So this is like the survey of select VOCs from like 200, and this is by, you can read up the paper by Zhu, yeah. Mm-hmm.
Thank you.
Thanks. Yeah, sorry that it was unclear.
Hi, I'm Steve Ginrich. I'm with UT Dallas in our innovation and commercialization area. And we're about to open with the city of Richardson a new 30,000 square foot space that has as part of it an installation of technology by a company called ActivePure with filters throughout that has a degree of FDA approval for some of their filtration technology. But what I'm interested in is the efforts that you and other colleagues, either here in Texas or elsewhere, are pursuing to get lower cost versions of your sniffer technology. Because we have low cost versions of sensors for external air quality monitoring, but I'd really love to see something low cost with high fidelity for the sniffer. So would love to hear your thoughts on what you're doing and what others are doing in that area. Thank you.
Thank you so much for this question. So definitely the idea is to also have low-cost sensors. The current challenge is to get sensors that have sufficiently low detection limits. So there are colleagues, for example, in mechanical engineering, for example, Professor Tanya Hatter, who is also here, and she specializes in those low-cost sensors. And we're actually even thinking about, for example, coming up with something like a biosensor that could detect mold. Because currently, if you go to the Amazon website, you won't find anything like this. It's really very challenging because to get a specific and sensitive sensor. And yeah, great question.